Good afternoon. Welcome to the Vienna Gödel Lecture 2015 of the Faculty of Informatics. My name is Stefan Seider. I'm your host for this afternoon. And before I have the pleasure of introducing our today's speaker, Peter Norvig, I give the floor to two welcome addresses. The first will be given by our Vice Rector of Research, Professor Johannes Fröhlich.
Okay, this is Vienna University of Technology, but now it works. Welcome to all of you. It's really a pleasure to be in such a sensationally attended lecture. So I'm chemist, and when there are lectures for chemists in our campus on the Getreidemarkt, so we are very happy if we have some 50 or 60, maybe 100 students and researchers, but this is not only proof that this is one of the largest faculties here, it's also one of the very active faculties, which I will maybe mention in a minute. So first of all, I would welcome you here. This is a pleasure to have you here. It's the third Gödel lecture, and it's another renowned lecture we have here, and obviously you can see these persons really attract audience and attract students, and I'm very happy that so many young people are here, because they are, so to say, the future of our society, and we really to foster the conditions for their education and also for their professional career in the future. As I mentioned, the informatics at our university is one of the very large faculties with many students, and also with so to say a lot of success within their research. It's within the US, I have noted here news rankings. It's on place 14 within the Europe universities, and what also is very interesting, within the Microsoft academic search, it's on place 10 in Europe, which is quite really a successful position. Our university is strong in quite some fields. We have strong quantum science, we have strong material science, but one of our real strong, so to say, pillars is informatics. From the discipline it's strong, from the research, but also from the cross-sectional, so to say, connection, because informatics and ICT is of course a very strong connecting science within other disciplines like mechanical engineering, chemistry, of course, physics, and as you know, we are very active in the industry 4.0 and cyber-physical systems. Professor Grosso, I guess he's somewhere, is very active here. So this is something where I think we have the best prerequisites also for, so to say, having good research in those fields. This is not only true for the university here, but also for the Vienna region and for Austria, but also in particular for Vienna. I would say Vienna is always known for Viennese waltz and for let's say, Heurigen and for tourism in particular, but it's not so known for ICT, because if you look to the economic data, then ICT is a multiple of value added as regarded to tourism in Vienna, which is very important, because sometimes always all these connections which Schloss Schönbrunn and all these, of course, very famous sites is seen. But actually, the future is in those fields where future people can get their job on and can develop into, let's say, very innovative jobs, innovative sciences. This is what I would like to mention, what I think is a really also good connection to your lecture here, and also to Google, which is also, of course, a very innovative company. This is what I really would like to say. So from this point of view, I think while you are in the right biotope here today now, I hope you will swim through this cloud with your lecture. I'm very looking much forward to your presentation. And with these words, I would like to hand over to the Dean of the Faculty, Professor Steinhardt.
Thank you. Ladies and gentlemen, friends and colleagues, As Dean of the Faculty of Informatics here at the Vienna University of Technology, it is my pleasure to welcome you all to this prestigious event, namely the third lecture of the Vienna Gödel Lecture series. What exactly is this lecture series? Every year, the Faculty of Informatics at the Vienna University of Technology invites an internationally renowned and inspiring computer scientist to share their insights with us. The purpose of this series is to show that computer science is key to developing the information and knowledge society of today and tomorrow, and to solving its complex problems. As many of you will already know, this lecture series is named after Kurt Gödel, a famous Viennese logician who emigrated from Austria to the United States in 1940 and continued his research at Princeton. But now I'd like to extend a very warm welcome to our guest speaker today, who has begun his scientific career on the opposite coast of the United States. Peter Norvig received his PhD from the University of California at Berkeley, where he continued his research for several years. Today, he is Director of Research at Google and responsible for an impressive range of innovative projects. Peter Norvig is one of the most distinguished and well-known computer scientists of our time. His scientific publications address issues in the fields of artificial intelligence and machine learning, as well as information retrieval, topics that are of particular importance for us here in the Faculty of Informatics at the University. His book on artificial intelligence is one of the most widely used textbooks in the field of computer science. But his research interests do not stop there. He has also concerned himself with new approaches to learning and teaching, such as MOOCs. Mr. Norvig, we are very excited to have you as our guest speaker here today, and we are all looking forward to your lecture. And for anyone who is interested in more in-depth discussion with Peter Norvig, he will also be appearing in discussion with Gerhard Widmer on how artificial is intelligence in the Heuer restaurant on Karlsplatz at 5 o'clock in the evening tomorrow as part of a Logic Lounge event. And now I'd like to hand back to Stefan Seider, who will say a little more about our speaker. Thank you.
Okay. I don't want to steal too much of the time for the actual lecture, therefore I will be very brief. Steinhardt already mentioned this book, and I have actually brought my personal copy. That's the, as Gerd Brewka called it, it's the AI Bible. It's now, I think, published some 20 years ago, and it's really the standard textbook in the field. And I think it shaped how we think and about artificial intelligence, and it shaped generations of researchers. And I think now the third edition has been published and the fourth is on its way. And I just recently learned that it's the fourth book of the 21st century. It's quite a remarkable thing, unbelievable. But okay, now as I said, I don't want to mention all the achievements and honors and awards from Peter Norvig. I just want to close on a very brief note that in addition to the technical content of his work, there is also his work exhibits that solving tricky problems is actually fun and enjoying. And this enthusiasm in Peter Norvig's work is also contagious. And many researchers kind of profit from this. Please join me welcoming Peter Norvig.
Wow. Thank you, Stefan, and everyone at the university for inviting me. Thank all of you for showing up and struggling through sitting in the aisles or standing on the sides or whatever, and I hope we can all have some fun. So let me say a little bit about Kurt Gödel. And so he was a logician, a mathematician, but I like to think that he would have been a computer scientist if only such a field had existed and if only there had been computers in the 1930s. So what did he do that deserved the title of computer scientist? One thing that Gödel did is he made a connection between the real world and the world of mathematics. So say in the real world, you noticed Anna is taller than Berta. You could write that in mathematics. And then another day, you notice Berta's taller than Carla, and you could write that in mathematics. And if you're only observing the world, you'd kind of be stuck. What else could you do just by looking at the world? But if you have mathematics, then you could put those two facts together. You could do a valid logical inference, and you could come up with a new fact. And then the amazing thing that Gödel really laid out is you can take that fact, and now you can project it down into the real world, and you can say, Anna is taller than Carla, without ever having observed that in the real world. So what Gödel did is he took this language of mathematics and he talked about this process of coming up with a proof. You take true facts in and true facts come out, and you can do something useful in the real world through this process of proof. And up to Gödel, that process of proof had just been mathematicians kind of waving their hands. And when they came up with something that most people agreed to, they said, now we're done. We have a proof. But what Gödel did was said, I don't want to just be swayed by rhetoric. I want to be absolutely sure. So he laid out a completely formal way of specifying that proof. And we did it with mathematicians then, and we called them proofs. But today, we have computer programmers, and we call them programs. And it's this very formal, there's no hand-waving in computer programs. It's got to be precise. And Gödel really laid the foundations for that. So that's great, and we can do a lot with programs. There's lots of problems we can solve and things we can do in the world. But there's some problems that we can't really solve, where the programmer is stuck, where they're faced with a problem that they don't know what to do with. So let's go back to the real world and think of a typical day for Anna. She speaks into her phone, says some words, and the phone recognizes her speech and does the right thing. And say she tells the phone, I want to listen to some music, and it starts playing songs, and it learns her preferences, and it plays the kind of music she wants. Let's say she goes into a supermarket, and the stock that's on the shelf, some computer system has learned what everybody in that neighborhood wants to buy, and they stock the right stuff. She pays with a credit card, and the credit card company has figured out, is this transaction a valid one? Is it fraudulent? Should I accept it or deny it? She posts a picture to a social networking site, and the faces of her friends are all recognized and tagged. And maybe she wants to plan a trip, and she asks for the most efficient route, and a website directs her exactly there. So she does all these things without thinking about it, but every single one of them has this property that the programmer wouldn't necessarily know how to do it. So I, as a programmer, I could solve a lot of problems, but I don't know how to recognize speech or recognize somebody's face and say this face belongs with this name and this face belongs with another name. I can't write down the steps to do that. And so I'm stuck. I couldn't solve that problem. So what do we do when the programmer can't come up with a solution? And the answer is computer to come up with the solution. If we as programmers can't do it, we can tell the computer to do it. And so what we do is we have, instead of having the programmers write lots of little programs, we have one big program that we call machine learning, artificial intelligence. It's got different names, and there isn't necessarily just one of them, but there's variations of them. And then we feed it some examples, and then the output of that program, rather than doing something, is it produces a new program. So it learns to write that program that we as programmers aren't smart enough to do. And then in the rest of this lecture, I'm going to show you some examples of what we can do with that. So, for example, making sense of word senses. What do I mean by that? Here's some example sentences. This is the word bank, and there's two senses of the word bank. There's the one having to do with money and the one having to do with the river. And one aspect of understanding language is you should probably know the difference between those two. We'd like to understand everything about those sentences, but I'm going to break it down and just solve that one little subpart of understanding language. And how are we going to do it? Well, we're going to feed some data into a program, and it's going to learn to write the program that will do that recognition. Because I don't know how to do it as a programmer. I don't know how to write the rules to do that. But I can gather up these examples. I can go search the web, find 1 million sentences that have the word bank in it, and throw that in. And then I can go to my dictionary and say, here's 2 definitions, and I can throw that in. And now I'm going to ask the computer, take those 2 things, list of sentences, list of definitions, and write me a program that will distinguish. And now I can feed it a new sentence, and it will say, this is bank 1, or this is bank 2. Now I'm going to tell you how to do that. So this is what it looks like. The sentences and dictionary definitions come in. We feed it into machine learning, and this program that decides the word sense comes out. And now I can take that program, and I can give it a new sentence it's never seen before, put my money in the bank, and it creates a brand new, or it creates as the output, I know which sense that is. So how do I do it? Well, I start with these definitions, because that's all I got to begin with. I got these definitions, and I take out my scissors, and I cut up the definitions into individual words, and I take each individual word and put it into a bag. Now, this is a very formal mathematical model. It has a technical name. It's called the bag of words model. So we got that bag. It's got some words in it. We shake the bag up. We do the same thing with number 2. We take all the words, we throw it into there. And so now we got these 2 bags. One's got those words in it, and this other bag has got these words in it. And now we're going to say, I need a model of how language works. So there's lots of tricky things going on in those sentences. They're talking about actions that are happening. They're referring to lots of words. It seems like I need to understand something about how language works in order to answer this question. And so I need a model of how language works. And I'm going to start off with the stupidest possible model I can think of. And one of my heroes, George Box, the statistician, said, essentially all models are wrong, but some are useful. So we shouldn't mind that the model is wrong. And so my model of language is, when you want to create a sentence, you pick out a bag that corresponds kind of to the kind of thing you want to say, and then you reach into that bag and you pull out a bunch of words and you put them together, and that's how people make sentences. Now, I know that model is completely wrong, but we'll see that it turns out to be useful. So I've got these 2 bags, and now a sentence comes in, and I want to say, who made this sentence? Was this sentence most likely generated by pulling words out of bag 1, or by pulling words out of bag 2? And we see, well, there's only one overlap. There's one word in there that comes from bag 2, so probably it's more likely that this sentence came from bag 2. So I could label it as that, and I would get this one right. But more importantly than getting this one right, I can now update my model and make it better. So I can take all the words from this sentence and throw them into bag 2. So bag 2 is now bigger. I keep on doing that, and the bags get bigger and bigger, and they've got bigger counts for the number of words they've seen. They've got a larger vocabulary corresponding to each word. So each bag is becoming a better model of making sentences about bank 2 or making sentences about bank 1. And basically, that's all there is to it. Everything I need to know, I learned from Sesame Street. We call him the Count. You call him Grafzal, right? Right. So here he is making a determination that this is sense number 1 for this word. Okay, so we've done that. We just feed a bunch of sentences through. We keep on making the bags bigger and bigger. And now we've got this program, this word sense decider program. I can give it any new sentence, and it can tell me, is this bank 1 or bank 2? And I can apply it to these sentences, and it does a good job. But let's measure, how well does it do? And the answer is, it depends on how well you train it. So if you give it 1 million words of training data, I go out on the web, I find 1 million words of sentences that have the word bank in it. And remember I said there was one yellow box called machine learning. Actually, I lied. And there's different schools of machine learning that prefer different techniques. And they publish papers that argue about whose technique is better. And one of the papers described 4 different techniques, and they got these funny names. They're all different methods of machine learning. We don't need to go into the detail, and said which one performs better. So when you give them 1 million words of sentences involving the word bank or whatever other word you want to decide about, this is the performance. The best one, the blue one here, does 85%, and the others are 80-something%. And so you might be tempted to say, yeah, well, the guys who are voting for blue, they're winning. But don't stop the discussion yet. Instead, we can go out and find 10 million words of training data, train it, and try again. And now everybody's doing better. In fact, everybody's doing better than any of the ones with 1 million. So all these people that we're arguing about, is my technique better than your technique, and who has a tricky new idea? Having a tricky idea isn't as good as just going out and gathering more data. And you can keep doing that. If you get 100 million words, it's better still. And now 3 out of the 4 were better than the best before. And when you get out to 1 billion words of training data, it seems like it's starting to asymptote out. We're not going to get too much more improvement. But now we're up to 97% correct. And we didn't know anything to start with. We had a terrible model of English. We didn't know anything about the syntax of English. We didn't know anything about the meanings of any of the words. We just had these 2 bags. And now we can solve this problem at 97%. And it turns out that a lot of problems have this type of characteristic response, that if you feed in a little bit of data to a very simple algorithm, it performs terribly. But if you get out into the millions and billions of examples, it starts to perform well. And you could say that Google makes its living by trying to find problems that have this kind of shape, and then trying to find the billions of examples that go with it, and then doing very well. Okay, so deciding between Riverbank and Moneybank, maybe that's not so impressive. Let's try to do something harder. Let's try to translate between languages. So translate between German and English or whatever. I live in California, so I'm going to do the example between English and Spanish. And here we have 2 examples of translation that I found on a sign. The red's a translation of the red, the white's a translation of a white. And I could go around looking at signs, but that'd be kind of slow. So instead, let's go to the World Wide Web, and let's find pairs of documents where one of them is in English and one of them is in Spanish. And we can go out, and there are ways of finding that. And in fact, we can find millions of such documents. And now what do we have? So now we have a set of labeled examples where I say, I know, here's the English translation, and here's a corresponding Spanish translation. Now, if anybody asked for exactly that sentence, I could just echo this sentence back, and I'd have a good answer. But of course, they're not going to ask me for exactly the same sentence I've seen before. They're going to ask me for a different sentence that I've never seen before, but hopefully it has some words and phrases that I know. So in order to make a good translation program, I'm going to have to break this up. And there are techniques for doing that to find where are the phrases that you see over and over again. And I won't go into the details for that, but just take my word for it, that you can break it up into pieces like this and say, I know that these are common phrases, and I know that this correspondence happens. How do I do that? Well, I look at millions of sentences and say, hey, in lots of sentences, they have this thing, security alarm in English, and they have this similar alarma de seguridad in the Spanish. And so maybe they go together, and once they go together, then it's easy to figure out the rest. And so we had the bag of words model before. This is sometimes called the refrigerator magnet model, because it's like moving around those little magnet words on a refrigerator. And it turns out this is basically it too. The bag of words model was all we needed for that task. This is all we need for this task. So what does the model look like? So it's not just counts of number of words inside a bag. It's a little bit more complicated. There's 3 parts to the model. So one, it still counts. One is there's this translation model that says how often have I seen one phrase correspond to another phrase, the total number of times I've seen that correspondence. Another is the target language model. So if I'm going to go from Spanish to English, I want to choose phrases that, but I also want to make sure I choose a good phrase of English. So I want a separate model of how often do phrases occur in English, and then I want to choose a good phrase rather than a bad phrase. And finally, there's this movement model that says not all languages have their words in the same order. Sometimes the words are moved to the right or left. And let's see, we see here these phrases did not move, but the phrase door moved to the right from English to Spanish, and the phrase is open moved to the left, and they move by 1 magnet difference. And so we put in our database that in this case, the door moved 1 to the right, and we keep track of all those movements as well. And we build up that model with all these counts in it. Now, when we see a sentence we've never seen before, we can apply this model. And how do we do that? So we take this sentence, I've never seen this sentence, I break it up into phrases, and potentially there's many ways I could break it up into phrases, because I've seen lots of those subphrases before, but I just choose one. Then I choose translations for each of those phrases independently. And again, there could be many translations for each of the phrases, but I choose one. Then I choose to move them back and forth. In this case, I've chosen 0 movement for all of them, so they stay in place. And then I consider lots of other choices. So at each of those points where I had a choice, I consider other choices and go through thousands or millions of possible choices. And then for each one, I kind of add up the score, basically count, but we want to be more sophisticated, so we call them probabilities rather than counts. We estimate the probability of each sentence, and then we choose the most probable. And that's the whole model. That's how we do translation. And of course, there are other tricks on top of that that make it a little bit more complicated, but you've got the basic idea. We just shove examples in, and an automatic translating program comes out. Okay, let's do another example. Recognizing things in pictures. I talked about recognizing people's faces, and if anything you wanted to do was recognize a face, then maybe you could have a programmer that was smart enough to figure that out. You'd measure the distances between the eyes and the distance between the nose and the mouth and so on, and maybe you could figure that out. But if you want to recognize lots of stuff, we don't have enough programmers to do all of that. So we got to do it with a machine learning algorithm. One of the resources that people in the image understanding community have is this site called ImageNet. And it has 20,000 categories of things and about 14 million pictures altogether of lots of different things. Here I've chosen some of the fungus categories. There's 300 different types of fungus. So you can tell right away that a machine learning program has a good chance of doing better than me, because I cannot differentiate 300 different kinds of fungus, and probably not many people in this room can either. But this system has got pictures of all of them. And I'll show you a quick preview of, this is from a paper from one of the systems, that machine learning system that was built on this, and they do really well at some of the categories. So red fox and Blenheim spaniel and so on, they're at 100% accuracy. But then there's other places where they're down in the 50 or 60% accuracy. And those tend to be the things that are more varied in their appearance. So apparently all Blenheim spaniels look pretty much alike. But water bottles, you know, have a pretty wide variety in what they look like. And those types of things are harder to learn. And I'm going to explain to you one way in which we try to learn, to try to do this type of identification of objects. And I'm going to do it by way of a parable. So suppose you were in charge of a store that made these types of tile mosaics. And you had a catalog with 100 different scenes that you could sell, and people would order that. But eventually you said, well, I want to expand my sales, and I want to get into the modern age. So I'm going to make a website where you can choose a file, upload your image, send it to us, pay us some money, and we'll make the mosaic and ship it to you. And that seems great. People love that. They want to make their own pictures. But then you realize, this is getting expensive. I'm making custom individual tiles for every single picture, and that just doesn't scale. It's too expensive to do that. What I want to do is I want to have an inventory of tiles and make lots of them ahead of time, because that's a lot cheaper. And then when somebody orders a picture, I'll reach into inventory, and I'll find the best pieces that match. And maybe they won't match 100%. Maybe they're just close. The customer won't mind. It'll be okay. Right? And so now the question is, if I had an inventory of a certain size, I'm only allowed so many pieces, what pieces do I choose? How could you answer that question? Well, one thing you could do is say, let's look at all the pictures people have uploaded so far, the pictures that they want to make tiles out of, and say, analyzing those, what sorts of things come up, and now I want to choose the best pieces to be able to make those. And if I can make those ones I've seen in the past, maybe the ones I can make in the future will come out the same. So this slide has the most math we'll see, so don't worry. If you can make it through this, we're home free. So what we're asking the computer to do is choose a set of pieces of a certain size, maybe 200 pieces we want to keep in inventory, maybe 100, maybe 1,000, it doesn't matter, but it's a set size of inventory, such that I can reach into that inventory and make near copies of every picture you want to give me. And I want to minimize the difference between the copy that I make and the original image. So it doesn't have to be exactly the same, but I want it to be pretty close. I want to minimize the sum. That sigma letter there means the sum. And then I'm going to allow myself, so unlike the tiles, I'm moving a little bit away from that analogy. And now I'm allowing each piece to be a combination of multiple pieces. So maybe it's more like stained glass than like tiles. So in one location of the picture, I can actually have the sum of several different pieces rather than having to choose only one piece for each spot. But the idea is, what pieces do I choose in order to make this task the easiest so I have the smallest error when I assemble a puzzle piece out of these pieces? And the hope is, the interesting thing here is that if I do that, then the pieces I've chosen, which sort of satisfy this mathematical equation, those will be pieces that represent what the world is like, what pictures are like, what things are out there in the world that people take pictures of and want to make tiles of and put on their walls. So it's a fascinating question. And when people first asked this question in around 2006, a group at Berkeley said, this might be an interesting way to do image processing. And it was fascinating. We wanted to know what was going to come out. If I have this certain number of pieces in my budget to represent the entire world, what does the world look like? And we got this answer. And the answer is that pictures are made out of lines. So kind of disappointing, right? But it shouldn't have been too surprising for people to know the history of image processing. So this idea of a vector, of figuring out the edge between one part of an image or another, that was always important in image understanding. And solving this equation just verified how important that was. So this is saying that these are the key pieces that this algorithm came up with. And it's saying all pictures can be duplicated approximately by taking a combination of lines and putting them together. And this was obviously for black and white pictures, not for color. Okay, so that's nice and kind of interesting, but it doesn't really get us anywhere, right? Now we've learned that pictures are made out of lines, but we already knew that in kindergarten, so we haven't gotten anywhere. So the next step came, it took about a decade, but we progressed to the next step, which was saying, rather than taking these pictures and creating one inventory of pieces, what if we had several layers? So what if we made an inventory of the smallest little bits and then combine those smaller bits into bigger ones, and then combine those into bigger bits still. And then what pieces would you put at each level? And in 2006, work by Hinton at Toronto and Andrew Ng at Stanford asked that question. And now, for the first time, the results got really interesting. So for their first inventory, it came out pretty much the same. They still agreed that pictures were made out of lines. But at the second and third level, we started to get some real results. And here they are. So if you put faces in, this algorithm now says, hey, you know what? There are things in the world that are eyes and noses, and then at the next level, there are faces. And so it picked these out of all the pixels in all the pictures. It said, these are the things that are important. And similarly, if you put pictures of cars in, you say, hey, there are doors, and there are wheels, and there are cars. And if you put a mixture of them in, it allocates about the right proportion of picture pieces to each of the kinds of stuff that's there. So this was fascinating. This was kind of the first time that a image recognition machine-learned algorithm actually did something that you could make sense of. And there was hope going forward. That was in 2006. By 2010, it was kind of the start of seeing practical results. And by 2012, it had taken over the entire field. So one of the experiments we did at Google is we took 10 million video frames from YouTube videos. We want to get to the point where we can do the whole videos, but right now we just grabbed individual frames, fed them in, and asked it, we'll give you a budget of so many pieces, tell me what you find. Out of all these 10 million YouTube videos, what are they like? What's out there in the world that's important? And the answer was, if YouTube goes in, then cats come out. All right, and if you squint a little bit, the lights here might be too high. I don't know if you can see this, but that's a picture of a cat, and this one's easier to see. That's a picture of a person. And then you can ask it, so these are 2 out of the 200 or however many puzzle pieces there were, and you can ask it, well, what do you identify with? What's the best match for you out of all the pictures? And it does a really good job of picks out the cats, and this picks out the faces. Right? So this system automatically, just from saying, here's what people take pictures of, it's decided that people think it's important that there are cats and people. It didn't put the label cat and people. It doesn't really know what they mean, but it knows from a physical image point of view that those are important. And here's another picture of what it's like. So this is the computer model we're building. It takes an image at the bottom. It extracts from that little pieces at the first layer and then starts feeding them up to the higher and higher layers. And by 2012, this was the ImageNet competition. So remember, there's 20,000, and sometimes it's going to be really, really hard to pick out the exact right category, right? If there were 300 types of fungus, getting the exact one right every time is really hard. So they tend to report on the top 5 error rate. So I'm allowed to guess 5 different types of fungus, and if I got one of them right, that counts. And so in 2012, this team by Hinton and Company did that in 16% error rate. Then in 2014, we had hired that team at Google and added some other people. You see the layers get a lot more complex, and now we're down to 6.6% error rate, and getting better all the time. Okay. So this is pretty exciting, that we can do well at a difficult task. We did it just by feeding pictures in, and we didn't have to do anything else. And this is a big advance because in the past, we had to spend a lot of time kind of training the algorithms by going through and labeling each one, by saying, this is a cat, this is a person, so on. Here, we didn't even have to do that. We just threw the pictures in and it figured out these categories. Okay, and now I'm going to just show one more example. And this is putting together these 2 parts that I've talked about. So I've talked about understanding language and understanding pictures. Now I want to do the task of doing both at the same time. So the training is I take a bunch of pictures that have captions, a few words or a sentence of text describing the picture. I gather millions and millions of those. I feed it into my machine learning algorithm. and it uses the kind of stuff we just saw, and it outputs a program which will now take a new picture that it hasn't seen before and generate a caption for it. And here's an example. So there's a picture, and we had different versions of our program. One version of the program said, close-up of a child holding a stuffed animal. Another version of the program said, a baby is asleep next to a teddy bear. And then we had humans rate them, and one said, a young girl asleep on the sofa cuddling a stuffed bear. So it seems like pretty good performance, right? So it's amazing how much is going on here, that this program, we just gave it examples of pictures and captions, didn't tell it anything else, and it's able to pick out the important stuff that in one case it called it a child, another case it called it a baby, and one case it called it a stuffed animal, another case it called it a teddy bear, and then it generated a sentence that looks like a pretty good sentence of English to go along with it. So that's pretty exciting, but of course, anytime you try something, there's always the outtakes. So why don't I show you some of those? Some of the cases where we didn't do as well. And there's an internal mailing list at Google or a website where you can submit your picture and then get the result, and if you think it's funny or interesting, you can post it. And so I went there and collected some. Here we have a flock of birds flying over a body of water. So, you know, didn't get it right, and you guys could do better. But then again, not completely terrible. Maybe if you've never seen a picture of fish from above, you can imagine how you might do that. Here's one. I don't know where this picture came from, but this is a couple of giraffes standing next to each other. And this is actually a real horse or donkey or something dressed in purple pajamas. And for some reason, out of the millions of training examples, we never hit one of those before. Here's one. Reflection of a dog in a side view mirror. Good doggy. You know, this one over here, you can sort of see that that's kind of dog size. So maybe that was okay, but ignored probably the most salient feature. And here's another one I like. A man riding a skateboard, right? And so out of all the pictures it had seen, you know, it had several pictures of people riding skateboards, and it had several pictures of people dancing or something, but it never imagined somebody like Elvis dancing like that without being on a skateboard. And also, I don't know how well you guys can see it from back there, but close up, you can see that there's actually parallel lines along the bottom here. So maybe that looks a little bit like the body of a skateboard, although the wheels are not present at all. Okay, so that was fun, and it gives you an idea that we're getting something out of this, but we're not quite there yet. We still need to refine these models. And then I want to show one more example, and this is a slightly different result in that everything I've shown so far has been what we call unsupervised learning and a little bit of supervised. So unsupervised learning is where you just show it a bunch of stuff as input, and the computer tries to come up with categories that seem salient. And supervised learning is when you show it a bunch of stuff along with a label saying this is the right answer. And now I'm going to show you the third type of learning, which is reinforcement learning, where you don't tell it this is the right answer, but you tell it you're doing well or you're doing poorly. So like when we train animals, we give them a reward or we give them a punishment. We call that reinforcement. This is reinforcement learning for computers. And the Google DeepMind team did this, and they took these Atari video games from the 1970s and taught a computer to play them. And so the input to the computer was just the pixels on the screen. They, in some sense, maybe cheated a little bit as they had a separate input, which was the score that you get in the computer game. They could have forced the computer to learn the score by looking at the pixels on the screen, but they said, let's bypass that and just feed the score in as a separate input. but that's all it knows. It's got access to buttons it can press. It doesn't know what those buttons do. It doesn't know what the purpose of the game is. It doesn't know what the representation of any of the objects on the game is. It just knows what the pixels are. And from that, it's got to learn how to play the game. And so this is an example of playing this game, Breakout, I think it's called, where you, one of the first computer games, there's a little ball that goes down. You have a paddle. You move it along. Now it's played 200 times. It's invested 200 coins in this game and lost every time. It's getting a little bit better. 400. Notice it's got this new technique now of kind of jiggling your paddle back and forth if you aren't quite sure where to be. So it learned that all on its own. Nobody told it that that was something it could do. Now up to 600. And at this point, it learns sort of the key strategy that separates the poor players from the good players, which is off on the left, it's digging a little tunnel, also trying to dig one on the right, and then does that cool thing where it bounces the ball off the back and gets a lot of points all at once. Okay? So it learned all this from nothing. All we told it was try to get more points. Now go out and play. You're on your own. And let me just close by saying this idea of machine learning is now everywhere, right? So I mentioned a few things in Anna's life, and here I've thrown up more, but everything you do in your life is now touched by these companies that are building stuff with machine learning that's trying to do a better job of understanding the world, of understanding what you want, of interacting with you, and we're doing it all by training the computers rather than by programming them. So let me stop now and open it up for questions.
Thank you very much. We have time for questions. Who wants to go first? Questions, comments? Yes, over there. Maybe. Can you get this?
Okay. What I wanted to ask is, are there any pairs of languages where the model you have shown doesn't work? Languages that are so different that
Yeah,
the model doesn't work?
That's a great question. So we built this system for translation. We have, I think, about 75 languages now. And we can do all pairs, so that's 75 times 74, about 5,000 or so pairs. And it's certainly true that some work better than others. And there's two aspects of that. One is, do we have enough training examples between the two language pairs, right? So we have lots of examples between German and English because people publish lots of those. We don't have a lot between Tagalog and Norwegian. And so for those, we do it through a process of multiple steps. So we take an intermediate language, it's often English, sometimes Spanish or Chinese, and we translate one into that language, and then we translate again into the other language. And you'd think that the errors would be doubled or squared or something like that by doing that multiple step. It turns out we're lucky, and usually most of the errors occur in the same place. So you get two errors in the same place, and then that only counts as one error, because one error replaces the other error most of the time. So it's not quite as bad as it seems. We're doing some experimentation with multiple paths to say, we could go from language A to B to C, but maybe we should also go from A to D to C and then combine those two in some ways, and that seems to help. But if we don't have enough data and we have to go multiple paths, that makes it worse. So that's one thing, is not having enough data. The other thing is if the languages are just fundamentally very different. And one thing is I showed this kind of refrigerator magnet approach where you're moving phrases around, and that really doesn't get at the whole idea. And so we're worse at languages that have to do more movement, right? So English is primarily subject, verb, object. In languages that have other orders, we do worse because we have to account for this movement model, and out of the 3 models I showed, the movement model is the worst, so the more you count on it, the more errors you make. That's one kind of way things can be different. Another kind of way is in how much you rely on individual words. So English is very good. We don't have a lot of endings on our words. Each word is fairly distinct. Other languages, Finnish or Turkish, tend to really bunch a lot of stuff into one word, and we sometimes make mistakes breaking that up, and that makes it hard. And then another difficult aspect is when you have to translate into a language that has more information than the source language. So in English, we don't have gender on our nouns, so we have a pronoun, we use it to refer to everything. But if we have to translate into German or some other language where there are genders on the pronouns, then we have to sort of invent one. And it's hard going in that direction because we don't know what it's referring to. If it's, we still translate one sentence at a time, and so if the referent for the pronoun was in the previous sentence, we don't have anything to go on. And so those are some of the aspects that make it trickier.
Back there, is it possible to get the mic to this question over there?
Hello. I just want to ask you, how long did it take the computer to learn how to play like this, and how much of capacity do you need for this? Like, can I do it at home on my Raspberry Pi, or do you need a mainframe server?
So, great question, and the answer is it's a wide spread of spectrum. So the DeepMind stuff, you saw that some of those were only in the hundreds or thousands of training examples, so that seems like it's not too bad. On the other hand, they did have, I forget the exact number, but some large number of computers available to them, hundreds or thousands of computers.
So it's like on a weekend done with your server capacity?
Yeah, right. And I think there's lots of interesting things you can do at home on your one laptop, right? So you've got enough storage to fit enough data to make it interesting. You make it past that hump in the curve where we pass the threshold. But the difference is if you've got one laptop versus a team that's got a data center, is they're going to be able to try more ideas, right? So your idea, you have an idea, you get it started, you go out, you have coffee, you have lunch, you have dinner, then you see the results. And whereas they can just snap through the ideas as fast as they want.
Thanks.
Thank you for an inspiring talk. My question is, where do you see machine learning in 2 or 5 years? And what are the brick walls you are heading right now? What are your problems, or where could you...
Okay, it's hard to predict, especially the future. We've seen so much in the last couple of years of this deep learning approach of feeding these things in through the various layers, and that's done so well. The issue is that it seems to work really well for these kind of perceptual problems of you have a stimulus and you want an immediate response. And so for playing a video game where you hit the paddle or looking at an image and just saying this is a cat, they're great for that. What they seem to not be so good at is ironically things that computers of the past were really good at. So these kind of long-term planning. So I didn't on are the ones that require more sort of long-term planning. So if you think of a game like Pac-Man, where in order to be successful, you have to first be able to run away from the bad guys locally, but you also have to decide, you know what, I'm going to take this path, and then I'm going to go up here, and then over here, and then over here, and then that way, and plan out that whole sequence ahead of time. These techniques can no longer do that. But we have other techniques that were really good at that could do that much better than humans can. You know, you go to one of these mapping sites and ask for directions from 2 points very far apart from each other, and it comes up with the exact optimal route. So being able to put that back in to gain some of the logical planning and combine that with this more probabilistic, fuzzy, perceptual work. And people are working on different approaches to try to combine those two.
On some of those slides you had a brain on the upper right corner. I was just wondering, are you trying to imply that this is how biological brains work, or is this something just an algorithm for computers purely?
Right. So that's the logo of the Google Brain team, which is doing these works with these neural networks. And I think it is a little bit confusing that we have this word, neural network, and on the one hand, it does have some analogies to the way that neurons in mammals work. But on the other hand, it's really solving this mathematical equation and coming up with the optimal result. And people sometimes confuse these two. To me, the part that I'm more interested in is just getting the right result by whatever technique possible. And so I don't really care so much if it's doing it the same way as the brain does or a different way. There are parts of it where it is really important to know what it is that the brain does. So, for example, the retina is probably best considered part of the brain, and we look very carefully at what the eye can do in terms of processing images and what's important and what isn't. So, you know, the eye has certain capabilities for figuring out the color in a scene, and it does a really good job of balancing that all out, unless it's a white and gold dress, and in which case it sometimes screws up. But everything else, you know, the eye has a sort of built-in capability to do that, and so we try to mimic that in our machinery because we want to match the way people see stuff. And so at that level, I think it's really important to understand the physiology. At the higher levels, I think we should not get confused, right? So it's certainly great to understand how people work, but that should be a separate task from understanding what's a good engineering solution. And you should be clear on which one you're working on at what time.
Dr. Norvig, may I ask you about your paper bags? The object which you identify and put in one of these bags, how you identify the object to the computer? As a binary bit string, or you had a number associated to each word? So what is the mathematical background? How you organize all your bits and pieces, and how you do give them internally a meaning or structure?
Right. So in that example, it was just individual words. So the words are the characters that you get from written text, separated by spaces, and then there's a number associated with each one. So it's just a count, what words did I see, and how many times did I see it. And in other problems, when you're dealing with representation of images and so on, we might have a different representation. But it's pretty straightforward, just copying what you see.
One piece is not identified only by how many times it is counted. Does it have another index number in your system that you say the bit car has a bit string, but also has 22? You put in, it comes 22. What is the numerical identity of this bit, of this piece, like car also, in your system?
Yeah, well, there's nothing broken up other than the fact that it's car is C-A-R, and that's distinct from other words that are spelled differently. There certainly are other approaches where we try to figure out what words are near each other. And there's this notion of word embeddings where we say, let's take a word and let's embed it in a multi-dimensional space. And there you do have this kind of bit string representations. But for what I showed here, it's just strict identity. Is this word exactly the same, or is it a different word?
Okay. Has the microphone arrived at the gentleman with the yellow T-shirt? Where's the mic? Oh, right. We only have 2 mics, sorry. Can you please help moving the mic? We'll then afterwards take 2 or 3 more questions. The next one will be here.
Okay. The methods you presented were all somehow based in numerics or statistics. Which kind of role do you think will play logic-based or more symbolic approaches in the future, or which role do they play now in your field of work?
Right. We couldn't come up with good conclusions because we couldn't come up with a proof, right? So it's all getting back to Kurt Gödel. He wanted to only know things that were absolutely mathematically true. And if A is greater than B and B is greater than C, then we know for sure that A is greater than C. But if I say Tweety is a bird, and then I ask, can Tweety fly? Well, I don't know for sure, because all I can say is, well, most birds can fly most of the time. But logic can't prove that this individual bird can fly or not. And so that's why we've kind of gone to probability, saying I can't answer that question. I can't give you a proof, but I can say, yeah, most likely most birds can fly most of the time. And that seems to be more useful for dealing with this messy real world.
Hello, thank you for the presentation. And I have a question. As you know, internet is growing and the data as well. And there are many trash in internet. And I want to ask you if Google is planning some in the future to something to separate the important data or to get out all the trash from the internet.
Yeah. We try. So I remember there's this law called Sturgeon's Law, after Theodore Sturgeon, who's a famous science fiction writer. And he was at one of these kind of academic conferences where they're trying to present science fiction writing as if it was real literature. And he made his case for that to be true. And somebody in the audience stood up and read some passages from really trashy science fiction novels and said, you know, isn't it true, Mr. Sturgeon, that 90% of science fiction is crap? And he says, well, of course it's true, but 90% of everything is crap. And that's probably true for the internet as well, although it might be 99.9%. And so I guess, you know, we don't want to, it's not our job to get rid of it, but maybe it's our job to help guide you through it. And we know we could always do a better job of doing that. But there are adversaries out there who really want their pages to be seen, and they don't think their pages are trash. They think their pages are important. And we're in a continual fight to try to defeat that, but they always have good methods, and so the fight will go on.
So here was the question, right?
So you just said that all the algorithms, we saw in your presentation that they're sometimes inaccurate, and you also said that it's a question of probability. Like most birds can fly most of the time, probably. So the question that I have is, with all the inaccuracy that is inherent in those algorithms, where do you see the risks for people? Like, we do know that certain agencies do have access to a lot of data, and they're using this data against people whom they deem like dangerous. And we do know that the algorithms they're using on the data are inaccurate, so there's a high probability there's failures which might be deadly for some people.
Okay. So let me answer that in two parts. One is inaccuracy in general, and then the second is these kind of privacy type issues, right? So inaccuracy in general, I think we need to evolve as an engineering discipline to say, we recognize that we don't have the right answer all the time, but how can we build systems that are reliable, that are made out of these unreliable components? And at Google, I think we've done a great job of that at the hardware level, right? So we have these with many thousands and thousands of computers in them, and parts of them fail all the time. The disks crash, the whole computer crashes, and yet we keep on going because we figured out ways to say, well, a component can fail, but the system as a whole will keep going. I think on the software side, the whole industry has not done as well. That we haven't quite figured out how can you build safe, reliable software systems. And we don't know how to do that for AI or machine learning systems. And we don't know how to do it for non-AI, non-machine learning systems either. And there are other engineering disciplines that have done a much better job, right? So if you look at civil engineers, right, it used to be you build bridges and sometimes they fall down. Now they hardly ever fall down. So the civil engineers have processes in place and you follow them very carefully and you get a good result. And maybe that means that they move slower, and the software industry is reluctant to do that, to say, you know, the customers have spoken. The customers have said, I really want the latest app on my phone now. I don't want to wait another couple months while you go through this long verification process to make sure it's perfect. I'm willing to deal with these errors. And you know, to some extent, you want to give the customers what they want, but for the things that really matter, maybe we should have more processes in place to be extra sure and prioritize reliability over speed of development. So that's what we got to do in terms of just dealing with these errors and inaccuracies. Then there's this separate issue of what about these privacy issues, right? So what about, you know, I don't care about some other error. What about when the error involves somebody thinking something about me that's not true? I think that's an important issue as well. That's probably more of a societal issue than a technology issue, right? So I don't think we can solve that by making the technology better. I think we have to solve that by having the rules and expectations of who uses what data for what better, and also the expectations for what you can do with the data. Just because you have a tool doesn't mean it always works. And I think we're seeing that problem. There's a privacy type issue. We're seeing this a lot in medicine and biology, where you know, if you go back a couple decades, if you wanted to develop a new drug, you had some idea, and then you did a trial. 100 people get this drug, 100 people get the other drug. You see who does better. It's kind of 50-50, who's going to do better, but we know how statistics work, and we look at the results of the experiment, and we decide this one's better than that one. Nowadays, we still have some of that, but we also have this kind of big data approach where we can say we've got these gene assay chips, and you can go through and you can do 1 million things at once. You know, look at 1 million different binding sites on these DNA strands and measure them all at the same time. And now the odds are no longer 50-50. Now the odds are more like 1 million to 1. So if there's one good one and you identify that, that's great. But if there's 10 bad ones out of 1 million, that seems like a really good rate, but it still means now there's 10 times as many bad results as there are good results. And as a field, I think we haven't learned to deal with that. Instead, what happens is rushes out and publishes a paper, says, great new cure or discovery for this disease, but then you go back and check and say, you know what, it didn't really work. It came out as a positive result, but it was actually one of these 10 false positives rather than one of those 1 true positives. And as a field, we have to learn to deal with that, when you're doing 1 million experiments at a time rather than 1 at a time, you're probably going to get more false positives, and you have to learn to toe down the rhetoric until you get separate independent verification. And I think that idea of independent verification could probably help out in the privacy domain as well as in the medical domain.
Okay. There's a whole lecture room of with people who watch this talk on a live stream.
Yeah.
And we also got many questions from there. But unfortunately, we come towards the end of the session. But so just one for all, I forward one question. Somebody asked whether Google is using AI techniques internally for things like financial planning or for recruiting and things like that.
Yeah. So we certainly, it's hard to tell where you cross the line between what's an AI technique versus what's data analysis, but we certainly do all of that, right? So we look very carefully at things like recruiting, that's certainly true. We look at all the resumes we get and who did well in interviews based on what features we saw in the resume, and then we follow that up by saying who did well once they were on the job. After a couple of years, did they perform as well as we thought they were going to do in the interview? One thing I can share is that was surprising to me is it turned out that being a winner of one of these programming contests was actually a negative factor for performing well on the job, which is surprising, and it doesn't mean you guys should stop doing the contest, but I think what it meant was everybody that gets hired at Google is pretty good. So if I just had to pick up somebody off the street, I really want that contest winner. I'm going to take him every time, or her. But if it's somebody who passed the hiring bar, then they're all pretty much at the same level. And maybe the ones who are used to winning the contest, they're really used to going really, really fast and cranking the answer out and then moving on to the next thing. And you perform better on the job if you're a little bit more reflective and go slowly and make sure you get things right. So, you can learn interesting things from the data that you wouldn't necessarily have known.
Okay, thank you very much. I don't advertise now this tomorrow the event at 5 o'clock at Café Heuer because I guess it will be hopefully overfilled. But I would like to thank you for this very interesting talk and for answering our questions. And please let's thank Peter Norvig for coming and giving us this interesting talk. Thank you.
Thank you.